Jai Hind everyone. Today I am going to discuss about the controllers. So what are the need of the controller, why we use the controller, and what are the different type of the controllers. I'll describe everything in this lecture. Okay, so what is controller? An automatic control system an automatic control system is used to maintain its output within the desirable limits, right? Any deviation in the output from the required limit is being detected by the error detector which is connected in the control system, right? The error which is detected is used as an actuating signal for control action through the controller. So basically these controllers are used for improving the transient part as well as the steady state part of any control system. So basically there are three types of controllers: proportional controller, integral controller, and the derivative controllers, right? Proportional controller is represented here by the P, okay? This is I is used for the integral controller and D is used for the derivative controller. So derivative controller can be used by two ways. If we can also apply the derivative controller in the forward path of any control system. Also we can apply the derivative control in the feedback path of any control system. So whenever the derivative controller is used in the feedback path, then we can call it as a tachometer or tachogenerator types of the controller, right? And by combining these controllers, we can also talk about the PIT controller. We can take the combination of two controllers also, PI controller, PD controller, and the above of all these controllers, the PID is the best controller because it is in calculating all the best properties of all the types of the controller. So we will discuss about these all these controllers in detail. So let's start with the proportional controller. So what is proportional controllers? As its name suggests, the proportional controller is proportional to the error signal. As I've already told you that the actuating signal is being generated by the error detector, and that actuating signal can be controlled through the controller, right? So here in case of proportional controller, the actuating signal is directly proportional to the error signal, right? This is the block diagram for the second order system, right? Here CS is the output of the system, RS is the input applied to the system, and this is error detector which is detecting the error. ES is the error signal generated from the difference of the reference input and the feedback signal which is obtained from the output here, right? So you can see in proportional controller, the actuating signal is proportional to the error signal. That is why the name is given to the this controller, that is the proportional control system. So, you know, it is required that the system must be an underdamped system, right? Why? For the quick response, right? Because an underdamped system is having exponentially decaying oscillations, right? In the output time response during the transient period, right? And this sluggish overdamped response can be made faster by increasing the forward path gain of the system. But there is a problem that if we increase the forward path gain of the system, the steady state error definitely improve, but peak overshoot increases, right? The steady state error will be decreased, but the peak overshoot increase. So a convenient adjustment has to be made in between the steady state error and the peak overshoot, right? So we can reduce the overshoot value to an extent that our steady state will not increase, right? So for this case, this is the block diagram for the second order control system. Here you can see that this US is the actuating signal here. Okay, so we can see here that US is directly proportional to ES. And we can write US is equals to Kp into ES. This Kp is the proportionally constant that is called as the proportional controller, right? Kp is indicating the constant for the proportional controller, right? So if we write it in terms of, this is for S domain, right? So this is the proportional controller, right? Now coming to the derivative controller. Derivative controller will include the error signal. Derivative controller will be the sum of error signal with the derivative of the error signal. That means here the actuating signal, that is I am representing here actuating signal by the EAS. Here the actuating signal will be the sum of error signal plus the derivative of error signal. Derivative of, let it be t in terms of t, det by dt. Okay, this will be small e, right? If we write it in the S domain, then here you can write it as EAS will be equal to E of S plus, this is TD is the proportionality constant, okay. So this will be S into TD into ES, right. So this is the block diagram for the second order control system having the derivative controller in it. So I can simplify this diagram like this. You can see this is the forward path and this is also forward path. So according to the block diagram reduction rule, these two will be added and I can write it as like this. So here this is the error signal which is generated from the difference of the input signal, that is reference input, and the output signal. So I can write here, this is the EAS and this is the forward path gain, and this will be the CS, and I can do it like this. So you can see here the EAS will be equal to ES plus STD into ES. That's what I have written here, right. Now from here you can see this is the GS, forward path gain, for this system, right. So we can take, we can find out the transfer function for this system, that will be CS upon RS will be equal to the forward path gain, which is will be equal to 1 plus STD into omega n square upon S into S plus 2 zeta omega n, okay, upon, since it is a unity feedback system, I can write it as 1 plus STD into omega n square, into omega n square upon S into S plus 2 zeta omega n, right. So when I simplified this transfer function, I got CS upon RS will be equal to, it gets cancelled out with this term and we will get 1 plus STD into omega n square upon, okay, this will be S square plus, this will be 2 zeta omega n plus omega n square into TD into S plus omega n square. So this will be the term, this will be the simplified transfer function, okay. It will be S square and this will be 2 zeta omega n into S, okay, here S, okay, and then this will be plus STD into, that means omega n square into TD into S, and this will be omega n square, right. So this is the denominator of any transfer function will define the characteristic equation. So the characteristic equation for this system will be S square plus 2 zeta omega n plus omega n square into TD into S plus omega n square is equals to 0, right. So if we compare this characteristic equation with the standard characteristic equation of second order system, we will get a new damping factor, zeta dash will be equal to 2 zeta omega n plus omega n square Td upon 2 omega n. Okay. Sorry. So I can cancel it out. Here 2 omega n cancel out. So this will become zeta dash will be equal to zeta plus this will be omega n square. Zeta plus omega n Td by 2. So I can write nu zeta will be zeta plus omega n Td by 2. So this will be the new damping factor. So if we introduce the derivative control in the forward path, then the damping factor will be increased by the damping factor will be increased by this term omega n Td by 2, right? So we can conclude that the damping ratio is increased but overshoot is decreased. So now the overall function, transfer function, can be represented here as this is the overall transfer function, which will be this. Overall transfer function can be written as this for this system. Okay, and let me write it once again, 1 plus STD. So overall transfer function it will be 1 plus STD omega n square upon s square plus 2 zeta 2 zeta omega n, okay, omega n Td into S, right, plus omega n square. This is the transfer function for the overall system, right? Okay, and the standard transfer function we know for the second order system will be this omega n square upon s square plus 2 zeta omega n s plus omega n square, right? So from here we have GS is equals to, what is GS here? So from here GS can be this will be the GS for this system when we have introduced a derivative system. So this will be the GS, that is 1 plus STD, right, into omega n square upon, so we can write it as 1 plus STD into omega n square upon S into S plus 2 zeta omega n. This is the STD, and we know that the ES upon RS for any system, for second order system, what is 1 plus GS HS. Okay, so from here I can put the value of GS, that is this, in this equation, and I'll get the error ES upon the ratio of ES upon RS, which will be coming out 1 upon 1 plus, this is 1 plus STD into omega n square upon S into S plus 2 zeta omega n. This is a 1 upon 1 plus STD into omega n square upon S into S plus 2 zeta omega n, right? Okay. Now if we solve this value, we will get ES upon RS will be equal to, if I solve it, I get this will be S into S plus 2 zeta omega n upon S plus S, this will be s square plus 2 zeta omega n s plus 1 plus std into omega n square. Okay, so this is the term. Okay, this is Es upon Rs, that is s into s plus 2 zeta omega n, okay, upon s square into s 2 zeta omega n s plus 1 plus std into omega n square. And for if input, if Rs is unit ramp input, that is 1 upon s square. Okay, then putting the value of Rs here, we get Es, and then we'll get the value of steady state error. So let's put the value here. So Es will be equal to Rs into, this is s into s plus 2 zeta omega n upon s square plus 2 zeta omega n s plus 1 plus omega n square td into s plus omega n square. This is the value, and we can put Rs here equals to 1 by s square for unit ramp system. So it is coming out to be, s will get cancelled here, and s plus 2 zeta omega n. Okay, so we cancel out this s, and we will be left with these terms into td into s plus omega n square. Okay, now steady state error will be limit s tends to 0 into s into Es. Now put the value of Es from here. So steady state error will come out to be limit s tends to 0. Here we have s plus 2 zeta omega n, okay, upon, okay, this is s into, sorry, this s will be here, into s square plus 2 zeta omega n plus omega n square into td into s plus omega n square. Okay, so this s get cancelled out with this term will become 0, and this is 0, this term again will become 0. Now we are left with, let me write it out here only, ESS will be equal to 2 zeta omega n in the numerator upon omega n square in the denominator. That means we are getting the value of ESS is equals to 2 zeta upon omega n, upon omega n. So you can see there is no change in the steady state error when we have applied the derivative control in the forward path. Okay, this is same before applying the derivative control and after applying the derivative control, the steady state error for the second order system comes out to be 2 zeta upon omega n. This is same. Okay, so we can conclude that the steady state error of second order system will remain same after applying the derivative control. But when we compare the transfer function of the second order system with and without derivative control, then we can see omega remains same, that is, but a 0 is added at s is equals to minus k 1 by t, which will result in a different expression for time response whenever the wherein the rise time is reduced. So hope it is clear to you the derivative control derivation. Now starting with the integral control, coming to the integral control. So what is integral control? Integral control action, the actuating signal will be the error signal plus the integral of the error signal. So we can write here, see, this is the actuating signal, EAT can be equal to ET plus the integral of the error signal, and the constant Ki is used for the integral control, right? So while taking the Laplace transform of this term, we will get EAS is equals to ET plus Ki upon S into ES. Sorry, this is ES. Okay. So we can write here this 1 plus Ki upon S into ES will be the actuating signal for the integral control method, right? So this is the block diagram of the system, second order system with integral control, right? So let me simplify this block diagram once again, as we have done in derivative control. This will be 1 plus Ki upon S. I am writing it on the basis of the block diagram reduction. Both are the forward path to this summation. So I can add these two values. So this will be EA of S, and it is coming out to be omega n square upon S into S plus 2 zeta omega n into CS. Okay, and this will be the unity feedback control system. So this is the actuating signal here. This EAS is the actuating signal. So from here I can write down the actuating signal will be ES into this term. So you can compare it with this. Okay, now I can write down, so this total will make the transfer function of the forward, will make the forward path gain. So CS upon RS can be written as this total is the GS for the system. Okay, so GS upon 1 plus GSHS. So let me write down this function CS upon RS. So the transfer function for the integral control will be CS upon RS will be equal to 1 plus Ki upon S into omega n square upon S into S plus 2 zeta omega n. Okay, upon 1 plus GSHS, that is 1 plus Ki upon S into omega n square upon S square plus 2 zeta omega n S. Okay, so when I simplified this transfer function, okay, what we will get? This term will get cancelled out with this denominator term, and I can write it as S plus Ki into omega n square, and this will be S plus Ki into omega n square, and this will be the whole term here. This will be S cube plus 2 zeta omega n S square plus, okay, S square plus S into omega n square plus Ki into omega n square. So you can see here, this is the characteristic equation which is a third order system, which is of third order, okay, which is of third order. So now this can be solved by using Routh-Hurwitz criteria, okay, Routh table, okay. So we will see the Routh criteria in next lectures. So here I am going to tell only the thing that, so when 2 zeta omega n is less than Ki, then two roots will have negative real part, right, and the system will become unstable. Positive real part, sorry. Then the two roots out of 3 will be having the positive real part and the system will become unstable. But if 2 zeta omega n is greater than Ki, okay, then all the three roots will be having the negative real parts and the system is said to be stable system. Okay. Now, error, I will calculate the error for this system in the next lecture, when we have applied the second unit ramp error or unit step error to the input to this type of system, then what will be the error. Thank you so much.